Hi, in this video we're going to have a look at Karnaugh maps, which is another way of representing a sample space. But I thought I'd start off with the starter problem first, which links into the previous video where we looked at mutually exclusive events and we also looked at some probability arithmetic, additive rule. So let's have a look at it. Given that the probability of A is equal to 0.2 and the probability of B is equal to 0.4 and the probability of A union B is 0.6, and then we've got two questions there. So pause the video, have a crack at it, and then return to the video. Okay, hopefully you did pause it, hopefully you did have a crack at it. Let's see how we go. Let's start off with the formula, which is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A union B. Now, if I substitute in, I get probability of A union B is 0.6, the probability of A is 0.2, and the probability of B is 0.4. And then we have the probability of A union B, unknown. Sorry, not A union B, A intersect B. I won't restart the video for this, I'll just quickly fix it up. And we can pretend that never happened. A intersect B, A intersect B. Okay, I didn't leave myself enough room here, so I'll just do it behind here. So as you can see on the left-hand side, my value is 0.6. On my right-hand side, I've got 0.6 minus the probability of A intersect B. So if I subtract 0.6 from both sides, I end up with 0 is equal to the negative probability of A intersect B, or the probability of A intersect B is equal to 0. Okay, and that is the condition for mutually exclusivity. Which I'll just put mutually exclusive here, but I could write, therefore A and B are mutually exclusive, i.e. the possibility of A and B happening at the same time is 0. There's 0 chance of them happening at the same time. So that's, like I was saying to you before, maybe something like I can go left or I can go right, but I can't go left and right when I get to an intersection. That's the example you said last time. Now, the second thing is draw a Venn diagram. So what the hey, let's do that. So I don't know if you recall, but when we draw our Venn diagram, like so, we don't have an intersection, and so they have to be drawn separately. Like this, if I can get circles instead of, there we go. So I would fill in A and B, like so, and then I'll fill in my probabilities. So I've got probability of A is equal to 0.2, so there's a big old 0.2 in there. The probability of B is 0.4, so I'll put a big old 0.4. Now that makes 0.6 in total, which means that the probability of neither A nor B is 0.4 out here as well. And we've got the probability of the universal set, as usual, equaling 1. And that's our Venn diagram, with no overlap because they're mutually exclusive events. Let's move on to the main learning for today, and I've got it set up already. It's on Karnaugh maps, sometimes called two-way tables, and we're stealing the example from page 338 in your textbook, 339. I'm just going to flick to that so we can see it. So here's example 17. Records indicate that in Australia, 65% of secondary students participate in sport. 71% are Australian by birth. They also show that 53% of students are Australian by birth and participate in birth. And then we have two things to find out: the probability that a student selected at random is not Australian, and that the probability that a student selected at random is neither Australian by birth nor do they participate in sport. So that's what we're aiming for. And a Karnaugh map, it really is just a reimagining of a Venn diagram. The reason why we might do it is because it pulls out specific information. It's looking at the either or, either they do or they don't, for two sets of information. You wouldn't normally use a Karnaugh map for 3 pieces of information like you would do in a Venn diagram, although you can do it. It's probably not worth the overheads that would be required. What you get instead with the Karnaugh map is a nice flat table which is a neat way of organising the information, and you get totals that you can utilise in order to solve problems fairly easily. So they're pretty quick to work out. So here we go. This is how we work out a Karnaugh map. You can see, first of all, that one of my sets of data, which we're calling sport, or S, is heads up each column here, S and S dash. Do you remember what the S dash stands for? It stands for the complement, so the not. So this is people who participate in sport, people who do not. People who are Australian by birth, people who are not form the rows. So one set of data becomes the columns and the other set of data becomes the rows. Now I'm going to use blue to write in the facts that we do know, and we simply look at the intersection. So for example, this and this would be people who play sport and are Australian by birth. Okay, and we're actually given that statistic already, so it's 53%. So I'm going to write it as a decimal, but you can certainly write it, I've got it in purple instead of blue, but that'll do. But you can certainly write it as a percentage instead, so 0.53. We also know that people who play sport make up 65% of those surveyed. So what that means is that this column here will add up to 0.65, so 0.65. Okay, so I hope that kind of makes sense. What else do we know? That's one more fact. Australians by birth are 71%. So I can fill this in here and put 7.71 here. Okay, so my purple is the facts that I've been given in the question. Now in red, I'll fill out the other columns. And basically all we're doing is wherever there's a missing gap, we can fill it with a number. So for example, between here and here, I can see there's a single gap, and so I can fill that in. However, here and here there are 2 gaps, and over here there are 3 gaps, and so on. So I can't fill out any more yet. But as I go through it, I can. So for example, this one must be 0.12. That'll make up 0.65. Yep. So there's one filled in there. Plus I've got another one here, 0.53, plus another let me see now, 0.2 will get me to 0.73, wouldn't it? So it must be 0.18. 68, 71, yep. Is another one figured out here, like so. So that's pretty good, but I've still got 2 gaps here and 2 gaps here. So I can't fill out any more, right? Because I can only fill out if I've got 1 gap. So what could I possibly do? Well, there is one more piece of information that I can fill in, even though it's not from a calculation like these 2 red are, and it's not from the facts that I'm given here. So again, have a bit of a pause and think, what value could I also fill in from this Karnaugh map? Did you come up with it? Did you get the answer 1? If not, it is 1, because ultimately both of these here are totals, and the total probability for a situation has to be 1, right? 100%. So there's a 1 there, and now that I've got that filled in, I can fill out quite a bit more. So for example, I can make that 0.29 there, and I can make this one 0.35, and then hopefully going this way or going this way, I'm going to get the same value here. It's probably good just to check it. So based upon the column, this should be 0.17, right? Because 18 plus 17 is 35. If I go this way instead, just to check, 0.12 plus 0.17 is 0.29. That works as well, thank goodness. So this looks like it's a decent locked-in set. So all of this information is pretty well much what we could do in a Venn diagram, but in a nice flat table. Now, there are a couple of questions that came from this, and that is that we had to work out the probability that a student selected at random is not Australian by birth. So if I go here and say a student selected at random is, oops, didn't really pay attention, is not Australian by birth, that would be the not A here, as I've got it there. So I will go, what is the probability of a not A? Well, it would be the total of this row here, 0.29. So the probability of not being Australian is 0.29 by birth, Australian by birth. And then the second one is, what's the probability that a student selected at random is not Australian by birth and does not participate in sport. So not that one, nor that one. So that would have to be not A, not sport. Okay, not Australian by birth, not a sport player. So if we look at the intersection of those two, in other words, where the two rows and columns converge, it's on this value here. And so we would say that the probability of not A and not S is 0.17. And that's basically it. So you're filling out a table and then you're solving problems based upon that table. Now, one last thing I wanted to do before I visited the, before I moved on, is to show you that a Karnaugh map can be translated into a Venn diagram, and the reverse is true as well, although I won't go through it in this video. But before I say any further, I just want to give you a key code word for this video, just to see who's paying attention to the video. And the key code word for this video is Rumpelstiltskin. So when I ask you in class, what's the key code, and you're able to tell me, there will be a prize as a result of having watched the video. So there. Okay, so if you think about it, this little moon section here is where I've got Australian students who were born in Australia but do not participate in sport. So born in Australia but do not participate in sport. That would be 0.18. So that's what would go there. This one here would be students who were not born in Australia but do participate in sport. So that would be sport but not born in Australia. So that would be 0.12. This one here, as we know, is the intersection. So that would be people who were born in Australia and also play sport. So that would be 0.53. And then the last thing we need to figure out is this bit here. And that is, that doesn't belong here, here, or here. And you can see 1, 2, 3 here. It's this set here that's missing. Okay, so I'll put my 0.17 here. And if I do add them up, I will get 1 as my total. Okay, so that's how you can sort of break it down. And again, you should be able to see that if I add these two together, 0.18 and 0.53, I would get this number here. If I added up 0.53 and 0.12, I would get this number here. So it all correlates together. Karnaugh maps and Venn diagrams, two different ways of representing a sample space.